So I want you to imagine you're standing in, like, the middle of a massive, just utterly pitch black cavern.
Okay, setting the scene, I like it.
Right. So you're in the dark and you click on a flashlight and the beam, it cuts through the dark and you can see a few jagged rocks nearby, maybe some dust motes dancing in the air.
Sure, just your standard creepy cave stuff.
Exactly. But eventually that beam of light just, well, it fades out into the black. There's more cavern out there, obviously, but your light can only reach so far.
Right, because flashlights aren't infinitely powerful.
Exactly.
Yeah.
And that boundary, the exact place where your vision just fails, it feels like a physical wall. But it's not, right? It's literally just the limit of your light.
Yeah, that's a really great way to visualize it.
Well, I was thinking about it because this is the exact paradox we're exploring on today's deep dive. Why does a universe that theoretically contains, everything, have a very hard 92 billion light-year edge?
It's completely wild to think about, because that illusion of the cavern wall, it applies directly to how we look up at the night sky.
And this is all tailored for you, the listener, by the way, because you reached out with a specific goal, right? You wanted to understand exactly how we observe space.
Yeah, the literal physical limitations of being earthbound observers.
Yeah.
I mean, by its very definition, the word universe implies everything that exists.
Right.
And if it contains everything, well, there can't be an outside, which means there really shouldn't be an edge.
But there is. Or at least it looks like there is from where we're sitting.
Exactly. From our perspective,
Yeah.
sitting on this little rock in space, we are absolutely trapped inside a very real physical boundary of observation.
So to map this out, we're pulling from a few different sources today. We've got an astronomy magazine piece on the physical bounds of the cosmos, a breakdown by Marcus Chown in BBC Science Focus. And we're also digging into the Wikipedia archives on this 2008 documentary called Journey to the Edge of the Universe.
We are essentially taking that flashlight, pointing it upward, and mapping out the absolute literal boundaries of what humanity can actually see.
But, before we can talk about where the edge actually is, we kind of need to understand how we even started looking for it, right?
Oh, absolutely, because the history of observing space is really just a history of our reality getting, exponentially larger in these very sudden, jarring jumps.
Right. It's not a slow progression. It's like, boom, the universe is way bigger now.
Exactly. If you rewind to, say, 1610, you have Galileo Galilei pointing a newly refined optical telescope at the Milky Way.
Which, before that night, people just thought was a cloud, right?
Yeah, up until that exact moment, humanity literally saw the Milky Way as it's just this continuous, fuzzy cloud of light that was kind of smeared across the sky.
It's just a painting on the ceiling.
Basically, yeah. But through that glass tube, Galileo realizes, oh, wait, this is to use his words, a congeries of innumerable stars.
That's congeries. That is such a 1600s word.
Right. But think about what that means. That wasn't just, a slight upgrade in optics. It was a fundamental shift in human reality.
Yeah, the sky wasn't just painted with a cloud anymore. It was suddenly filled with individual physical suns that are separated by just vast, vast distances.
And then, 3 centuries later, we build telescopes massive enough to realize that our entire Milky Way, all those countless stars that Galileo saw, well, that's just one of many island universes.
Which is what we call galaxies today.
Right. And today, modern orbital observatories, they can look into these tiny patches of seemingly empty dark sky and reveal that our observable universe contains roughly 2 trillion galaxies.
2 trillion, 2 trillion is a number the human brain just straight up rejects.
We really cannot conceptualize that scale. It's impossible.
Which is probably why we constantly try to, shrink the cosmos down into a narrative that we can actually digest.
Oh, for sure. Which brings us perfectly to that 2008 documentary from our sources, Journey to the Edge of the Universe.
Yes. Okay, so this was a massive broadcast event at the time. Did you know, depending on where you lived, you actually had a different celebrity cosmic tour guide?
Wait, really? I didn't know that.
Yeah. In the U.S., it was Alec Baldwin. In the U.K., you got Sean Pertwee. And if you were watching in Canada, it was Paul Assembre.
That's hilarious. But the film itself, it really attempts to give the viewer this visceral sense of that 2 trillion galaxy scale.
The hook is incredibly ambitious. It basically uses early CGI to create the illusion of this single, continuous 91-minute camera shot.
So you just never cut away.
Never cut away. You start on Earth, and the camera just flies outward, completely unbroken, all the way to what the film identifies as the edge of the universe.
And they depict that edge as the Big Bang itself.
Yeah. It's essentially a cosmic wood trip. But okay, I have a major pushback here based on what we're trying to learn today.
Let's hear it.
The documentary portrays the Big Bang as a physical destination, right? Like you can just travel to it at the edge. Is that actually how it works when we point our telescopes into the dark?
No, not at all. I mean, the cinematic framing works great for television, but it fundamentally misrepresents the physics of observation.
Because it treats the Big Bang as if it were a place in space.
Exactly. As if you could just put a spaceship in hyperdrive, fly in one direction for long enough, and eventually you just hit this wall of primordial fire.
Wait, because the Big Bang wasn't an explosion that happened in space, right?
Right. It was the explosion of space. It happened literally everywhere at once.
That is so hard to wrap my head around.
It is. And more importantly, telescopes don't work like spaceship windows. They are, quite literally, time machines.
Because of the speed of light.
Yes, light has a universal speed limit, which is about 186,000 miles per second.
Right, so when I look at the moon, I'm not seeing it as it is right now.
No, you're seeing it as it was about 1 second ago, because that's how long the light took to cross the gap between the moon and your eye.
And when I look at the sun, I'm seeing it as it was 8 minutes ago.
Exactly. And John Mather, he's a Nobel Prize-winning cosmologist who was super instrumental in the James Webb Space Telescope. He points out that astronomers only observe the observable.
Meaning what, exactly?
Meaning, when we build these massive orbital observatories to peer into the deepest, darkest patches of space, we aren't zooming in on a place. We are simply catching ancient light that has been traveling for billions of years.
So we are just looking backward in time.
Yes, looking outward into space is identical to looking backward in time.
Okay, but if we are looking backward in time, we eventually have to hit the beginning of time, right?
We do. When we look out to the absolute limit of our instruments in every single direction, we do hit a visual wall.
The edge of the cavern.
Yes, we see the leftover fading glow of the Big Bang itself. It's called the cosmic microwave background radiation, or the CMB.
The CMB, okay.
So about 380,000 years after the Big Bang, the universe finally cooled down just enough for the first atoms to form.
Before that, it was just too hot.
Way too hot, just a dense fog. But when it cooled, it allowed the first visible light to finally travel freely through space.
Wow.
And that ancient flash of light is still washing over us right now, today, in the form of microwave radiation.
So that is our visual edge.
That is it. It is not a wall in space. It is a horizon of time.
Okay, so if the visual edge is just a limit on how far back in time we can look, how big is the actual physical space we are currently looking at?
Well, let's look at the numbers.
Right. Our sources note the universe is 13.82 billion years old. Since light has a strict speed limit, it can only have traveled toward us for a maximum of 13.82 billion years.
So logically, if you just use basic math, that would mean our observable universe is a sphere with a radius of 13.82 billion light years.
Which Marcus Chown, in that BBC Science Focus article, he grounds this with an analogy that perfectly describes our limitations.
Oh, the ship analogy. I love this one.
It's so good. He compares it to standing on the deck of a ship out in the middle of the ocean. You look around and you see the horizon forming a perfect circle around you.
Right, but you don't assume the ocean just ceases to exist beyond that line.
Exactly. The horizon is just the limit of your sight line. It's dictated by the curvature of the Earth.
And in cosmology, we have a cosmic horizon. It's our sphere of visibility.
And beyond that horizon, there are likely endless oceans of galaxies, but their light simply hasn't had enough time to reach our ship.
We are entirely trapped within our own local cosmic horizon.
Right.
But, and here's where things get really weird, the mathematics of that horizon present a massive contradiction.
Right, because I was reading the source material, and the observable universe isn't a 13.82 billion light-year sphere.
Yep.
According to the actual measurements, the bubble of space we can currently see is a staggering 92 billion light-years across.
Yeah, quite a bit bigger.
But if light has only been traveling for roughly 14 billion years, how on Earth can the sphere be 92 billion light-years wide?
To solve that geometry problem, we have to look at the mechanics of an expanding universe.
Okay, wait on me.
So, rewind to 1915 during World War I. Albert Einstein publishes his theory of general relativity.
Classic.
And when physicists applied his gravity equations to the entire universe, they found a huge problem. A static, unmoving universe would inevitably collapse inward on itself due to gravity.
Everything would just crush together.
Right. So to counteract gravity, the universe had to be in motion. It had to be actively expanding.
And Edwin Hubble actually proved that mathematically in 1929, didn't he?
He did. He looked at distant galaxies and realized they were all moving away from us, and they were moving away from each other.
The BBC article vividly describes those galaxies flying apart like pieces of cosmic shrapnel from a titanic explosion.
That's a great image.
Right.
But the expansion wasn't just this steady, uniform crawl. In the first fraction of a second after the Big Bang, the universe underwent a violent phase called inflation.
Inflation, right.
And during inflation, it stretched at a rate far faster than the speed of light.
Okay, wait. I always get stuck there because the fundamental rule of physics is that nothing can travel faster than the speed of light.
That is the rule. Nothing can move through space faster than the speed of light.
Ah, through space.
Yes, space itself is not bound by that speed limit. The actual fabric of the cosmos can stretch and expand at any speed it wants.
That is a massive distinction.
It is. And today, that expansion isn't just continuing, it is actively accelerating
Accelerating, why?
because of a mysterious force we call dark energy. It's constantly pushing outward, stretching the very fabric of the universe.
Oh, if I'm picturing this right, it's like a digital photograph on a computer screen being endlessly upscaled.
Okay, yeah.
Like the individual pixels which represent the galaxies, they aren't actually migrating across the screen. Instead, new space, like new blank pixels, are constantly being inserted between them.
That is exactly it. The space itself is what's growing.
Wow.
So while the light from the oldest, most distant galaxies has been crawling toward our telescopes for nearly 14 billion years, the empty space between us and those galaxies has been relentlessly stretching that entire time.
Oh, I see.
By the time that ancient light finally hits our lens, the physical galaxy that originally emitted it has been pushed far, far outward.
The track basically stretched out from under the light.
Yes.
Yeah.
That stretching is the exact reason why our observable bubble spans 92 billion light years instead of 14.
Okay, but if the space itself is growing and stretching, the natural follow-up question, the one everyone wants to know, is what is it expanding into?
Ah, yes.
I mean, if the track is stretching, what is outside the track?
That might honestly be the most common misconception about cosmic expansion.
Oh, really?
Yeah. When we picture expansion, our earthbound brains immediately imagine an explosion happening inside a massive, pre-existing empty room.
Right, like a grenade in a warehouse. We picture the shrapnel filling the void.
Exactly. But there is no room. There is no pre-existing void. Space itself is the medium.
So the distance between objects is just increasing.
Yep. There's no outside room for it to grow into.
But if there is no outside, what is the actual shape of this expanding space? Because our sources detail 3 theoretical geometries for the universe.
Right. Based on how space curves under the influence of gravity and matter.
Okay, so what are the 3 shapes?
Well, the math allows for 3 possibilities. First, space could have a negative curvature, meaning it bends outward, sort of shaped like a Pringles chip or a saddle.
A saddle.
Got it. Second, it could have a positive curvature, bending closed like a sphere.
Okay.
Or third, it could have absolutely zero curvature, meaning it is entirely flat.
Now, a spherical universe is by far the most intuitive for us, right? I mean, we live on a spherical planet. We orbit a spherical sun.
It makes sense to our brains.
Yeah, a spherical universe would be closed and finite. It basically means that if we built a hyper-advanced spaceship, picked one straight direction, and just kept flying for billions of years, we wouldn't hit a wall.
Well, you just keep going.
We would eventually loop all the way around the universe and return to Earth, exactly like Ferdinand Magellan's crew circumnavigating the globe.
Exactly. It's a finite space with no edges. And it is a conceptually elegant model. Einstein actually favored it. He called it a finite yet unbounded universe.
Yeah.
But observational astronomy really doesn't care what we find intuitive.
No, it rarely does.
Right. So starting in the late 1980s and continuing through the 2000s, cosmologists launched these orbiting observatories specifically to map that cosmic microwave background radiation.
That fading horizon of time we talked about earlier.
Yes. And they weren't just taking pretty pictures, they were trying to measure the geometric shape of the entire universe.
Okay, wait. How do you measure the shape of the entire universe using leftover light from the Big Bang? That sounds impossible.
It's brilliant, really. They do it by looking at the physical sizes of the tiny temperature fluctuations in that plasma glow.
The temperature fluctuations.
Yeah, the CMB is covered in these incredibly subtle hot and cold spots. And because physicists understand the acoustic sound waves of the early universe, they know exactly how large those hot and cold spots physically were back then.
Okay, so they know the actual size of the spots.
Right. So they use those spots as the base of a massive cosmic triangle.
Oh, I see. So they draw a triangle from Earth all the way across the observable universe to the CMB, and then they measure the angles of the light traveling toward us.
Yes, exactly. Now, if the universe were shaped like a sphere, the light rays traveling from those spots to our telescopes would converge and bend inward,
Like a magnifying glass.
exactly like a magnifying glass. So the spots would appear artificially large to us, meaning they'd take up greater than 1 degree across in the sky.
But if it were saddle-shaped?
The light rays would diverge, making the spots look artificially small.
Okay, so what did they actually see?
When the observatories mapped the sky, the spots appeared exactly 1 degree across.
Which means...
They appear precisely the size they should be if light travels in perfectly straight, unbending lines.
So zero curvature.
Zero curvature. To the absolute limits of our most sensitive instruments, the universe is definitively completely flat.
Wow.
John Mather basically equates it to an endless, infinite sheet of paper. You could travel forever in any direction, never hitting an edge, never looping back, just finding more and more galaxies endlessly.
Okay, wait, hold on. If we are comparing the universe to a flat sheet of paper, well, a piece of paper eventually has an edge where it gets cut, right?
Right.
How can we make this huge leap from the observable part is flat to it goes on to infinity?
Well, we can't. We can't definitively prove infinity, and honestly, that is the fundamental frustration of studying cosmology.
It's maddening.
Virginia Tremble, she's an astronomer, quoted in our Astronomy magazine source. She states it so plainly. She says, "The universe has always been slightly larger than what we can see."
Oh, that's a great quote.
Yeah. We simply cannot observe infinity. We can only observe our local 92 billion light-year bubble.
You know, it's kind of like ancient civilizations concluding the Earth was flat because their local patch of dirt looked flat.
Exactly.
They couldn't see the curvature of the entire planet from where they were standing in a field.
Right. The Greek mathematician Eratosthenes, he actually had to use the angles of shadows in different cities to prove the Earth was a sphere.
Right. You can't just trust your immediate vision.
And today, cosmologists are using the shadows of the CMB, but those cosmic shadows are telling us the universe is flat.
But it could still just be a localized flatness.
Yes. If the universe actually is a sphere, it is a sphere so unfathomably massive that our 92 billion light-year bubble is entirely too small to detect the microscopic curve of its surface.
So we are just left with a flat universe, which can either be infinite or finite with some incomprehensible boundary that we just cannot see.
That's the limit of the flashlight in the cavern.
So if our literal vision hits a time horizon wall and our geometric measurements max out at flat and maybe infinite, what do we actually do next? I mean, we can't just throw our hands up and stop looking.
No, of course not. When direct physical observation hits a hard limit, science just pivots to mathematical theory.
We build models.
Exactly. Think about the standard model of particle physics.
Oh, right.
The mathematics of quantum mechanics predicted the existence of the Higgs boson particle decades before we ever built particle accelerators powerful enough to actually observe it in a laboratory.
Because the math described everything we could observe so perfectly, physicists trusted it to predict the things they couldn't see yet.
Cosmologists rely on the exact same principle. We build mathematical models of relativity, of dark energy, and quantum fluctuations.
And hope they point the way.
Yeah. If those equations eventually map our observable universe flawlessly, they might offer the indirect mathematical proof of whether our flat universe stretches on for infinity or if it has a true physical limit. We trust the math to illuminate the dark cavern where our flashlights finally fail.
It is amazing how the scale we've mapped out today fundamentally changes how you look at a night sky.
It really does.
I mean, we went from Galileo realizing a fuzzy cloud was actually a cluster of distant suns to Hubble discovering those galaxies were racing away from us.
A huge jump.
And we learned that the edge of our universe isn't some physical wall depicted in a CGI documentary, but a cosmic horizon of time, you know, the 13.82 billion year limit of ancient light reaching our telescopes.
And due to the stretching of space itself, that horizon encloses a 92 billion light-year bubble of zero curvature flatness.
It is just a dizzying amount of space.
It is. But, there is one final mechanical reality of this expansion that really puts our fleeting existence into a profound perspective.
Okay, what is it?
Well, we established earlier that the expansion of the universe isn't just continuing, right? Dark energy is actually causing it to accelerate.
Right, the new pixels being added faster and faster.
Yes. Because that expansion is actively accelerating, the empty space between us and the furthest observable galaxies is now stretching apart faster than the speed of light can travel across it.
Wait, If the space is growing faster than light can cross the gap, then the light from those galaxies is losing the race.
Yes, it will never reach us.
Oh my God.
Right now, at this very second, distant galaxies are slipping over our cosmic horizon. Their light is being outpaced by the stretching of space, and they are disappearing from our observable universe forever.
That is terrifying.
Tomorrow, the observable universe will literally contain slightly less for us to see than it did today.
Just a little bit darker.
Yeah. And in the extremely distant future, as dark energy pushes everything further and further apart, any civilization looking up at the night sky, they won't see 2 trillion galaxies.
What will they see?
They will see nothing but an empty, pitch-black void. They'll have absolutely no way of knowing about the massive, chaotic, populated universe that we get to witness right now.
Wow, we just happen to exist in the exact sliver of cosmic time where the universe is illuminated, close together, and observable.
We're very lucky observers.
Well, thank you for joining us as we pushed our flashlights to the absolute limit. For you listening, the next time you step outside at night and look up, remember that the dark isn't empty. It's just full of light that hasn't reached you yet, or light that has already slipped away. Keep looking up, keep asking the big questions, and we'll see you on the next deep dive.